How could that be? How could any well-organized, rational enterprise have produced that result? So I figured I needed some evidence. Now, I just want to say how I got this, because I was going to talk about this misunderstanding of Einstein's worries about quantum theory. And I thought, well, everybody, this is so common, I just need to Google. And I Googled the two words Einstein dice. And on the first page, the fourth hit was this video. Now, this video is produced by the Institute of Physics. So it's a very kind of big mainstream physics organization that put together a nicely produced explanation to the general public about Einstein's worries about quantum theory. And so I hope this will be loud enough. Let me get it as loud as it'll go and see if I can. Well, I don't know if the microphone is just recording. Now the question is, how do I get it started? Oh, here. No. I know I can do it. Come on. It just went over. Start. Nope. Sorry. Here we go.
So the everyday world is governed by classical mechanics, and that is completely deterministic. Now you might be thinking, why do we use probabilities when we, say, throw a dice? Well, that's actually just because of lack of knowledge about what's going on. You don't know exactly how it was thrown, where the perspectives of the table are, etc. But in theory, if you knew all that, you could work out exactly what number is going to come up every time and win all the money in the world when you're gambling. The problem is when you go to quantum mechanics, the level of the atomic and subatomic, things are a bit different and a bit weird and sort of fuzzier, let's say, because all you can actually work out is the probability that the thing you're looking at is going to be in a certain state. And that's not because of a lack of knowledge, that's just how it is. Now, Einstein didn't like this idea at all, and that's why he said God, who presumably is all-knowing, doesn't play dice. Except quantum mechanics agrees with experiments extremely well, and even people who have tried to make so-called hidden variable theory, which means there is sort of a secret proper state that we don't know about, can't seem to do it. Bell's theorem actually says it's impossible. So I'm afraid, Einstein, it looks like God does play dice.
Okay, so Einstein didn't like quantum theory because it's not deterministic, and Bell proved you can't have a deterministic theory that returns the predictions of quantum mechanics, right? And that's standard, what probably most physicists believe. All right. So, I mean, the first thing to notice, given that he said that, when I Googled this, I wasn't even looking for Bell, right? I was just looking for Einstein, and Bell, he popped that in. That was just an extra thing at the end, right? So, again, maybe everybody knows this. Bell, supposedly the guy who proved you can't have a deterministic hidden variables theory that reproduces the predictions of quantum mechanics. What did he actually say about the pilot wave picture, which is exactly such a thing? You've probably seen this quote telling us that it ought to be taught to every physics student so that they can see, as he says, the vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice. So Bell obviously didn't think he'd proven the impossibility of deterministic hidden variables, just the opposite. Right? He thought it was a very promising, one of promising, and he was, as we'll hear, Bell was wonderful about recognizing the potential for clearly formulated theories and ways of understanding quantum formalism, and it was, both with the Bohmian mechanics and then with the GRW theory when it first came out. He saw what it accomplished. Okay, what about Einstein? What about this idea that what Einstein hated about quantum theory, the reason he couldn't accept it was because it was indeterministic. He was just some old fogey, too caught up in classical ideas, couldn't get with the program. You've probably all heard this. Well, and when I say there's been a systematic attempt to distort this, I'll tell you something about this quote. This quote should also, the beginning of it will be familiar, hopefully, to all of you. from Giancarlo's book. So it seems hard to sneak a look at God's cards, but that he plays dice and uses, quote, telepathic methods as the present quantum theory requires of him is something I cannot believe for a moment. Okay, so sneaking a look at God's cards is Giancarlo's book. But here's another fact when I was looking this up. This was some time ago when I was looking this up. What I found was that on the web, more times than not, you do not get this entire quote. There's an ellipsis. The part that's been cut out is and uses telepathic methods. Okay? So what you read reinforces the myth. But that he plays dice, as the present quantum theory requires of him, is something I cannot believe. Okay? Now, what Bell understood, and what's perfectly clear, and I'll give you again a little more evidence, was that the indeterminism wasn't really what bothered Einstein. It was the telepathic method stuff. And it bothered him about the standard theory, about what we would call Copenhagen, which is more or less equivalent nowadays. Some people don't use the word Copenhagen, but they say, oh, I believe in operational quantum theory. You may hear that. It's more or less the same thing. And the same comments will apply. Okay. So here's, again, a letter from Pauli de Born. This is quoted by Bell, and makes the same point. In the middle, Einstein does not consider the concept of determinism to be as fundamental as it is frequently held to be, as he told me emphatically many times. He disputes that he uses as a criterion of admissibility of a theory is it rigorously deterministic. So, Einstein also is sitting there yelling at people, no, that's not the problem. Okay? That's not why I don't like quantum theory. All right, so the reason he really didn't like quantum theory was, as he said, the spooky action at a distance, right? And the place where that was first laid out, but unfortunately in a way that was not as elegant and concise as it might have been, and maybe involved adding some extra parts that lead to some confusion, was in the Einstein-Podolsky-Rosen paper. So all I want to do when I say EPR and NEAT, I mean without any extra frills, I'm trying to present the argument in a way that doesn't involve any other complications. The EPR argument does depend upon a locality principle. It employs a locality principle. Part of the problem, looking back, is that it seemed so self-evident, this locality principle to Einstein, that he doesn't make a big deal of it. He doesn't focus on that. And so, again, if you're not paying enough attention, you might misunderstand what his target was. So if you think, you can read the paper and think, oh, his target is showing that you can beat the uncertainty principle, or that you can overcome complementarity or something like that. And that's really not the point of the paper. Where the locality principle appears in the paper is when they apply their famous criterion for an element of physical reality. Now, this is also something I'm going to talk about for a while, because it's not unusual, and I'm just speaking from experience here. It's not unusual to come across physicists who say, well, of course I don't accept the conclusion of the EPR paper because I reject their criterion for an element of physical reality, right? Their paper relies on this criterion, so if I just say, I don't like your criterion, then I can ignore everything else in the paper. And much of what I want to do, again, is just to say that's not actually an acceptable response to the paper. There are acceptable responses, but that's not among them. Why not? Because the criterion, and this is the one little bit of philosophical jargon I'll use here, is what philosophers call analytic. which means the truth of it follows just from the meanings of the words, like a logical truth. And so you can't say, I'm going to reject that. It's not a claim of physical principle or physical fact. What you can dispute is not the criterion itself, but you can dispute whether in a particular concrete situation the criterion applies. And that is something if you want to reject the conclusion of EPR, which was that the quantum description of a system is not a complete physical description, you can reject that conclusion by saying the situation they describe is not one where the criterion applies. But that's going to involve something to do with locality. Okay, so here's the passage where they introduce the criterion. And again, if you haven't gone back and read the paper and you just sort of hear about it secondhand, it's useful to notice how careful they are here. I mean, they're careful to say, for example, what they're giving you is a criterion. I mean, they say they're not giving you a definition of physical reality, of what it is, what it is that makes something real, or what are the conditions better, what are all the conditions under which we would have to recognize that there's an element of physical reality. They certainly say here, it's nice, they say you can't determine it by a priori philosophical considerations. So you have to look at the physics and you have to look at the world to have a reasonable claim to show that something is real. But instead of, if they gave you a definition, then it would cover all cases. They're rather just giving you a criterion, which is a sufficient condition, but not a necessary condition. And it's the thing that they've italicized. If without in any way disturbing a system, we can predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Okay? And they say, notice, they say about this criterion that it's in agreement with classical as well as quantum mechanical ideas of reality. That's also true. You often hear, if people say, well, suppose you give me the quantum state of a system. What physical properties does that system have? And one answer you'll hear is, oh, well, you have these operators. Those somehow, the operators represent possible physical quantities. And the condition for the system to have a particular quantity is that it be in an eigenstate of that operator. And the value is then the eigenvalue. And that's, of course, also exactly the situation where you can predict with certainty what the outcome of a measurement will be, right? When it's in an eigenstate. So this is in line with what even standard discussions of quantum mechanics would say. Now, my claim is that the thing italicized here is not something you can reject. And you just have to reflect on the meanings of the words in it. I mean, they say here, the one thing, if I could rewrite this paper or give them a suggestion, it would be that they say the criterion they regard as reasonable, which sounds like you can reject it. Because, okay, it's reasonable, but still, maybe I can make an argument or something. But I think it's more than reasonable. It just follows from the words. So why does it follow from the words? Well, because it has in it this word disturb. If you can predict without in any way disturbing a system. Well, what is it to disturb a system? It's to alter its physical state. If you do something and you say, whatever I just did not alter the physical state of some system, then you would not say you disturbed the system. Okay? So suppose you do something and it doesn't change in any way the physical state of a system. And on the basis of doing it, on the basis of that procedure, you can now predict with certainty how that system will behave in some experimental condition. Then all they're saying is, first of all, there must be some physical characteristic of that system that guarantees it'll behave that way. That's just to say we're doing physics, right? I mean, you're saying it has a physical feature. And that physical feature must somehow be determined by its physical condition. And since the procedure didn't disturb the system, it must have had that feature before I did my procedure, right? Because my procedure didn't change it. In particular, my procedure didn't bring that physical characteristic into existence. And it must have that physical characteristic independently of even whether I do the procedure or not. Because again, the claim is the procedure doesn't disturb the system. So what Einstein, Podolsky, and Rosen conclude is that even if I'm just in a position in theory to make this determination without disturbing the system, then the system must already have some physical characteristic, one which I could, if I so cared, find out what that characteristic is without disturbing it by doing this procedure. So I don't see anywhere one can object to this criterion. Okay? So first of all, if I do the procedure, then I found out what that characteristic is. The characteristic was already there because I didn't disturb it. And then the further thing is, even if I'm just in a position to find out and do this procedure, then the characteristic must already be there because doing the procedure, again, whether I do or don't do this procedure doesn't make any difference, physical difference to the system. And that's all just built into the word disturb. Good. So I don't think you can somehow attack the criterion. What you can do is say, in a particular concrete situation, you have to ask yourself, does the criterion apply in that situation? Because it involves this condition that your procedure doesn't disturb the system. If you do a procedure that does disturb a system, then the criterion tells you nothing. Right? It doesn't tell you anything one way or another about what the elements of reality are. Okay? And so really the question is, how do EPR argue that a certain procedure doesn't disturb a given system? The way they do it is by using remoteness in space and time as an insulator against disturbance. Right? So that's the fundamental assumption. And that's a locality assumption. Right? It's just the assumption that if two systems are far enough away from each other in space and time, no procedure carried out on this one can immediately alter. I'll give you a kind of slightly more precise version of what this locality, condition of locality that's assumed by EPR is. Okay. So this is my way of putting it. This is not what they say. It's got some fuzzy words in it, but you'll see they're fuzzy in the right direction. That is, they're fuzzy in a way that if you deny what I call EPR locality, then it's all the more striking what you're saying must be going on, right, if EPR locality does not obtain. So EPR locality just says that according to the theory, if you carry out some procedure in one region, that whatever those procedures are, they do not immediately disturb the physical state of systems in sufficiently distant regions in any significant way. Now, the fuzzy words here are sufficiently distant and in any significant way. Okay? How far away does the other system have to be insulated against disturbance? Well, the theory should tell you there at least should be some distance, right? If a mile isn't enough, make it 1,000,000 miles, okay? If you say, according to my theory, there is no distance sufficient to insulate it, that's pretty striking, right? What does in any significant way mean? Well, again, maybe you do something over here and it does disturb this system, but not much, okay? And you say, well, how little? Well, suppose I can make that disturbance as small as I like. Then it still is EPR local in my sense. I'll give you an example. So if you're going to deny that a theory is EPR local, what are you saying? You're saying there are some procedures carried out in one region do immediately disturb the physical state of systems in extremely different, arbitrarily distant regions and in a significant way. Right? It's a significant disturbance. It's a big disturbance. It's a disturbance you could notice. It's a disturbance that could make a difference to how an experiment carried out in that other system comes out. Okay? So if you deny EPR locality, I think Einstein's words that you're signing on to spooky action at a distance is quite well founded. Now, the way I've just defined it, every classical theory, even Newtonian gravitational theory, so often you'll hear, oh, Newtonian gravitational theory had, of course, some spooky action at a distance or some action at a distance in it, and that's why people didn't like it and this and that. Notice the way I've just defined it, even no matter how you understand it, Newtonian gravitational theory does not have spooky action at a distance. In fact, as I said, no classical theory had it. And this is for two different reasons. Sometimes they both apply. One reason is spatial attenuation. So let's grant for the moment that Newtonian gravity is instantaneous, is an instantaneous action at a distance theory. Right? A mass here produces a force arbitrarily far away on every object in the universe instantaneously. Newton, by the way, did not think that. This is not Newton's own view of gravity. He didn't think gravity worked like that. He thought gravity worked by some kind of particles, and he didn't know what they were and how they behaved, and that's when he says hypothesis non fingo. Right? I'm not going to frame any hypothesis about what's causing this force. But he said enough for you to know that he didn't think it was action at a distance. And he said enough for you to know if he thought it was particles going from, for example, between objects that was carrying the gravitational force, enough to know that he wouldn't have thought it was instantaneous either. There would have been some time of flight. But he doesn't go into that. And for his purposes in doing planetary theory, it's essentially a static gravitational field, so the time delay wouldn't matter. If you got into fine details of objects orbiting each other and you can't treat either one as at rest, then that time lag would actually make a difference to the predictions. Okay. But the point is, gravity is an inverse square law. So it attenuates, and if you get far enough from some system, then nothing you do to it will have a significant gravitational effect, right, on the distant system. So that's why we can, otherwise we would have to take account of every piece of mass in the universe to make any predictions in Newtonian gravitational theory. So the attenuation by distance makes that theory EPR local in the sense that I've put out. The other reason that theories are EPR local, classical theories, is this time lag, because there's immediately in there. The effect of this procedure is supposed to be immediate. Well, if there's a time lag, if you need time for an electromagnetic wave to get from here to there, or for the particles to get from here to there, then the further apart you get the systems, the greater the time lag, and the more you can be sure that doing something here isn't going to disturb the thing over there in this window of opportunity where you're doing an experiment far away. Okay? So for that reason as well, I say Newton actually would have expected there to be such a time lag for gravity, and then you would fall afoul of the immediately part if there's such a time lag. Good. Okay. So let's suppose the world is EPR local, the actual physical world. Then, if you're in this situation and I can do two experiments arbitrarily far apart, and the theory tells me that the outcomes will be perfectly correlated, then it follows, if we accept, right, if it's an EPR local world, doing this experiment doesn't disturb the state of the other system, but by doing this experiment and applying the correlation predicted by the theory, I can predict the outcome of the other experiment, and therefore there has to be an element of reality pertaining to each system that determines the outcome. Right? Because we can experimentally make this determination. And by the criterion, we're saying one experiment didn't disturb or alter the state of the distant system. Now notice, just this, for a single, the place where the EPR paper gets a little overly complicated is, in the EPR paper they set up this entangled state between our two particles where there's a perfect kind of correlation between the positions and a perfect anti-correlation between the momenta. So you can run this argument both for position and for momentum. But that's not important, right? In order to make their point, don't worry about that. Don't worry about the fact that you can do it both for position and momentum. Just notice that you can do it just for position. That is, by making a measurement of the position of this particle, I can now predict with certainty what the outcome of a measurement of the position of that particle will be. If the world were EPR local, then there'd have to be something about the distant system that determines the outcome of that position measurement. But the point is, the initial quantum description of the pair does not attribute such a property, right? The initial entangled state is not an eigenstate of the position operator and does not tell you what the outcome of a position measurement will be. So if by the EPR criterion you can say, but there is a piece of physical reality over there that determines that, then you've already got, without mentioning momentum, you've already got the conclusion that the quantum description is not complete, which that was the title of their paper, is the quantum mechanical description of reality complete. Okay? So if the world were EPR local, the measurement on one side would not disturb the state on the other. Therefore, there's a position measurement element of reality of the distance system that's not reflected in its quantum state. And then you can run the same argument, if you like, for momentum, because the anti-correlation in momentum gives you the same situation. And then you can argue that, gee, not only does each particle have to have, as it were, a definite position, it also has to have a definite momentum, and then you can say, gee, that violates the uncertainty relations and blah, blah, blah. But that's just all add-on, right? The argument would still go through without all that extra stuff. So, EPR leaves us with a dilemma. If we accept the predictions of the quantum formalism that give us these perfect correlations, then either the quantum description is incomplete or the actual physics of the world is not EPR local. Now, Bohr and so on, one thing, it's a little bit hard to understand their reaction to this. It was never quite clear, but one thing that was clear was they wanted to insist that the quantum description was complete. And if this is our dilemma, right, either incompleteness or non-locality, and they're absolutely clear they're not giving up on the completeness of the quantum theory, then they're committing themselves implicitly to non-locality, to spooky action at a distance. Thus, standard theory, right, the Copenhagen interpretation, and the same thing goes for operational quantum mechanics or anything you like, commits itself by insisting on already, just at EPR, just by the EPR argument, commits itself to a kind of non-locality. Okay? And that's how we get Einstein's remark that in the standard account, God both plays dice, since there's no pre-existing element of reality, and uses telepathic methods. Now, and notice they're linked, right? It's because God plays dice that he also has to use telepathy. In the EPR case, you could get rid of the non-locality, but only at the cost of getting rid of the indeterminism because of the perfect correlations. Right? So the EPR paper certainly does not prove, and Einstein didn't think it would prove, that there was spooky action at a distance. It just proves that if you take the standard account of quantum theory, you're committed to spooky action at a distance. Now Schrödinger, and I'm not sure again how well known this is, the famous Schrödinger cat paper was written in response to the EPR paper. And Schrödinger was really quite shaken. When he writes the paper, he says, I'm not sure whether to call this a report or a confession. And he extends it. So he notices that they're maximally entangled states of two systems such that any measurement I can make on this system, I can accurately predict the outcome of that measurement by doing a procedure on the other system, an appropriate procedure on the other system for anything. And so if the world were EPR local and what I do over here doesn't disturb the state over there, it follows that there would have to be elements of reality that determine the outcomes of everything I could do over here. Right? So you would have, as it were, have to have determinism of every observable property. Now Schrödinger illustrates this in this very beautiful analogy. So he says, imagine I've got a bunch of school children and they're trained in this weird way, right? I have a whole bunch of questions I can ask them. I don't know the answer to the questions, but there's a book over here that has the answer to every question. 100 questions, and I have a bunch of students. They've all been through some training program, and here's the way they behave. I can arbitrarily pick any of these 100 questions and arbitrarily pick any of the 100 students and ask them that question and check in the book whether they gave the right answer, and they always get it right every single time. Every single time I do this experiment, okay? For every question. Now Schrödinger says there's an odd thing, which is that after I ask the first question, the student gets confused or tired and can't answer any further questions correctly, okay? He said, that's kind of weird. But okay, that's kind of weird. So asking the question somehow freaks them out. But it doesn't affect, he says, it doesn't matter that they can't answer further questions. Still, that the answering the first question so tires or confuses the pupil that his further answers are worthless changes nothing at all of this conclusion. He says, the only thing you can conclude is that every student is prepared to correctly answer every question, right? Because I can arbitrarily pick a student and arbitrarily pick a question, and they always get it right. So every student has to have been, the only other possibility is some conspiracy that, no, this student only knows the answer to question 43, and somehow when I pick them, I always somehow magically pick question number 43. That's crazy, right? So Schrödinger notices, and this is not something, from the EPR thing, of course, then you say, look, if you reach the conclusion that every student has to be able to answer every question, so there's, as it were, a corresponding element of reality, then in the EPR case, I can check position on one side and momentum on the other, and then use the correlations to attribute across the thing, and then get a position and momentum attribution for each particle, right? And so here's what Schrödinger says. There's no doubt about it. Every measurement is for its system. The first measurement on separated systems cannot directly influence each other. That would be magic. Neither can it be by chance if from 1,000 experiments it's established that virginal measurements agree. But he says the prediction catalog, and this is, I get the Q is one system, the little q and p are one system. I measure, say, position on this system and get 4, and then I measure the momentum on the other system and get 7, and then I predict -7 here. And then he says, well, that would be hypermaximal, right? I've now attributed both a position and a momentum. That would violate the uncertainty relations and everything. There's no quantum state that'll give me that. So Schrödinger understood perfectly well. The point is, what EPR says is, look, it's either determinism or spooky action at a distance. And Schrödinger said, look, it's either magic, that's his word for spooky action at a distance, or hypermaximality, which is, there are more facts here than the uncertainty relations allow. Now, after Schrödinger, now I'm not even going to try and go through Bohr's response to the paper. There we are in 1935. Einstein understands what's going on. Schrödinger understands what's going on. But we don't get Bell, right, for almost another 30 years. So there's a really interesting question, because we're, as it were, on the edge of what Bell did. But obviously, there was some very large conceptual block to get over. Probably the most interesting thing that happened in between was just rewriting, when Bohm, in his textbook on quantum theory, rewrites the EPR argument in terms of spins. Because Schrödinger considered making different measurements on the two sides, but the only case he considered was position momentum. And in position momentum, there's no correlation at all, right? Finding out the position doesn't change your predictions for the momentum at all, right? So there's no information. And if you ask, well, what about, as it were, all the other possible things you could measure besides position and momentum? Formally, they're well defined in the theory, but practically, it would be very hard to tell an experimentalist, right? So, think of, there must be some quantum observable that corresponds to position plus momentum, right? You take two Hermitian operators and add them up. But if you say, here, go to an experimentalist, here, measure this.
You did also explicitly consider harmonic oscillator energy values.
That's right. He did. So there were some things. But most of the things wouldn't be. But once you put it in terms of spin, it's obvious how you measure all the different spins. All you're doing is reorienting your magnets in space. So the idea that you should check not only what are the correlations when the things are perfectly aligned and what are the correlations when they're orthogonal, but what are the correlations at all intermediate degrees? It's going to occur to you once you reformulate this in terms of spin. But of course, even that isn't going to get you there, or Bohm would have discovered what Bell did. So that brings us, now let me just recap everything. So Einstein's complaint about standard quantum mechanics is not that it's indeterministic, but that it requires a form of non-locality. The form of non-locality that Einstein worried about obviously has nothing to do with actually sending signals in any practical way, right? He never thought, he said, insisted, standard quantum mechanics is shot through with spooky action at distance, but he certainly never thought that means you can send signals, or he would have worked on the theory and said, here's how you do it, right? And in fact, it's obvious that the actual EPR correlations you can reproduce without anything that would allow you to send any signals. So that's not the meaning of non-locality for Einstein. It has nothing to do with signaling, or he wouldn't have been on about it. The correlations that Einstein looked at don't require action at a distance, because you can recover the phenomena without any spooky action at a distance, but only in a deterministic theory. And that's the point of the Bertelsmann-Sachs case, which, again, if you do this, you will find people who don't understand Bell in a horrible way mangle the point of Bertelsmann-Sachs. Bertelsmann, as you know, I guess, always put on different colored socks in the morning. So when you see one sock, that provides you information about the other sock, but there's nothing non-local in that. But what Bell says is, quite correctly, there's nothing non-local because they have their colors all along, right? They have their colors when he put them on in the morning. If you believed, which would be a weird thing to believe, that Bertelsmann-Sachs, neither of them has any color at all until you look at it, then you would be really puzzled, right? I mean, first of all, you'd be puzzled about how you're looking at the sock manages to bring a color into existence. But you'd be even more puzzled that somehow looking at one sock and bringing its color into existence then alters the other sock so it can't assume the same color, right? Einstein, of course, thought you could find an EPR local theory that would recover all the predictions of quantum theory, at least all the verified predictions. And by the EPR argument, in settings like the EPR setting where you have these perfect correlations, it would have to be a deterministic theory. And although, and this is now the main point, Einstein seemed to prefer both EPR locality and determinism, EPR locality was the more important to him, right? That was the thing that bothered him about standard quantum theory, was that it did seem to have to deny EPR locality. So now we get to Bell, right? So after 30 years, Bell has the advantage of Bohm's rediscovery of the pilot wave theory, which is a demonstration that you can, of course, recover determinism if that's what you want. But, and this is in the paper that Bell wrote before the famous paper, the one that was published afterwards. So he says, in this theory, in the pilot wave theory, an explicit causal mechanism exists whereby the disposition of one piece of apparatus affects the results obtained with a distant piece. In fact, the Einstein-Podolsky-Rosen paradox is resolved in a way in which Einstein would have liked least. And that's absolutely right. You want determinism, I'll give you determinism. If you thought what Einstein wanted was determinism, then he would have been happy. Einstein would not have been happy. Because, and Einstein had been playing also with similar theories, and I believe, we think, discovered that he couldn't come up with one that got rid of the non-locality. That's why he didn't like them. He certainly didn't like Bohm's theory. He said it. If all he cared about was determinism, he would have loved the theory. Now, another little comment here. When I submitted this paper that's going to be published, I got 2 referee reports. One of which saying it was a piece of trash and should never be published. And the other of which was nice, it was a pleasant thing, but it was an interesting thing because the person said, you know, I'd completely forgotten that the title of Bell's paper is on the Einstein-Podolsky-Rosen paradox, right? That's the title of the paper. So if you want to say, I want to understand what Bell was doing, the first thing you want to do is go back and think about what the Einstein-Podolsky-Rosen paradox was, right? And people, you know, sort of know Bell did something, but good. So here's the first paragraph. As I said, my whole talk is just basically about the first paragraph, but now we understand the importance of it. The paradox was advanced as an argument that quantum mechanics could not be a complete theory, but should be supplemented by additional variables. These additional variables were to restore, right, to restore to the theory causality and locality. So notice, restore, right? Quantum theory is not causal, that is deterministic, and is not local. I'm trying to get the locality back. In this note, the idea will be formulated and shown to be incompatible with the statistical predictions of quantum mechanics. It is the requirement of locality, or more precisely, the result of one experiment on one system be unaffected by operations on a distant system with which it has interacted in the past, that it creates the essential difficulty, right? What you can't get back, you can get back determinism if you want it, you can't get back locality. We are stuck with non-locality. What are the presuppositions of Bell's proof? Well, the accuracy of quantum predictions. There's an assumption when you do the proof of EPR locality, as I've described it. And there's an assumption that your experiments are essentially random samples from the actual, if I have a collection of systems and I do experiments to collect statistics, that I can think of those as being random samples out of the whole collective. That's it. From the accuracy of the quantum predictions, in particular the perfect correlations or anti-correlations, and from the assumption of EPR locality, you find you have to say that there are elements of reality that predetermine the results of experiments on one system and that obtain independently of what experiments are carried out on the other system. And from the assumption of random sampling, we get that the observed statistics of the outcomes must be pretty close to the actual statistical distribution of in this whole collective, even though we can't check all of them in all the systems. The main mathematical observation is just that there's no possible distribution of such local elements of reality that can have the observed statistics. And that's just a mathematical fact, right? There are 2, I'll go just quickly through 2, I guess everybody knows this, but because, again, you often hear there's some kind of weird presuppositions. I said, when the response to my paper, what Werner says is that I and Einstein and Bell all make yet another presupposition we're unaware of that you can deny, a preposition he calls classicality or realism or something like that. He gives it a bunch of names. And he does the favor in his response of saying what that presupposition is. So according to him, the presupposition that I make and that Bell makes and that Einstein makes, and that if you deny undercuts all of these arguments, is the following presupposition: that the state space of the theory is a simplex. That's what he said. It's going to be published. It's nice. It's there on paper. that the state space of the theory is a simplex. Now, if you can find in the arguments I'm about to give you anywhere the assumption that the state space of my theory is a simplex, please raise your hand. Okay? I mean, that's a condition. It's not, in quantum theory, it's not true. The state space, at least of all the density matrices, don't form a simplex. But the point is, it's not a presupposition of the argument. Einstein never presupposes that. Bell never presupposes that. So let's just look at what's the argument. Well, we look at polarization. We know that if we're checking polarization on appropriately entangled photons, that the photons will either both pass or be absorbed by their polarizers, cosine theta squared of the time. So they'll agree, they'll either both be passed or both absorbed 100% of the time when they're aligned, 75% of the time when they're misaligned by 30 degrees, and 25% of the time when they're misaligned by 60, just by plugging in cosine squared theta. The 100% correlation means we're in a position by doing a measurement on one or an experiment on one to predict with certainty the outcome of an experiment done on the other. And so if it's an EPR local theory, all of the results must be predetermined by elements of reality. Okay? So that's what the EPR argument tells us. If you've got an EPR local theory, then all of these have to be predetermined. And then, as you know, there are different ways of proving this. This is the one I like, where people, you know, it's one of many. You say, look, suppose they're all predetermined. Each photon is just like the other, predetermined in what it's going to do if it meets a polarizer set at a certain angle. Suppose at 30 degrees you have a stream of collection of pairs. In this pair, both of them will be absorbed, both of them will be absorbed, both of them will pass, and so on. Let that be whatever you like, right? Fill in this middle row however you like. The mathematical requirement is that if I were to check at 30 and 0 rather than both at 30, you would get 75% agreement. So that means I can only change 25% of these letters from middle to top. And if I check at 30-60, I have to have 75% agreement. So I can only change 25% of the letters from middle to bottom. But if I only change 25% going this way and I only change 25% going that way, then there have to be at least 50% where they still agree on top and bottom. But you tell me if I check on top and bottom, there's only 25% agreement. So it's just mathematically impossible. Yeah. Okay, good. That's perfect. The other nice example you've probably heard is this beautiful example of Greenberger, Horn, and Zeilinger, where you don't even have to worry about statistics. You have a triple of particles in a certain entangled state. You can subject each of the particles either to an X-spin measurement or a Y-spin measurement. The predictions of the theory is that if you check 2 X-spins and a Y-spin, whichever ones you like, there'll be an even number of up results. If you check all 3 Y-spins, there'll be an odd number of up results. So that's just the prediction of the theory. And these can be done as far away from each other as you like. So if the theory is EPR local, the result of each possible experiment must be predetermined for each particle, irrespective of what, if anything, is done to the others. So your job is to put U and D into these 3 circles. So this would tell you whether, if I check the Y spin on particle 1, I get up or down. If I check the X spin on particle 1, whether I get up or down. You have to put U or D in these 3 circles so that I have an even number of U's along the blue lines and an odd number along the red line. And this is, you know, Merman said this in a very nice way. It's easy to see that's mathematically impossible. Suppose you've done it. You have these little chips with U's and D's on them. Then if I pick them up, I pick up an even number when I pick up those 3 and throw them in a hat, an even number picking up those 3 in a hat, an even number picking up those 3, throw them in a hat, an odd number of U's picking up those 3 and throwing them in a hat, even, odd. I have an odd number of U's in the hat, but I picked up every single one twice. Can't be done. Just mathematically impossible. Okay, so that's it. That's what Bell did. Right? He showed that no EPR local theory can replicate the predictions of quantum formalism for for experiments done far away from each other, and ultimately we'll say it's space-like separation. In relativity, we can make this sort of precise. What we mean, thinking relativity should certainly isolate these systems from one another. Therefore, if the predictions of quantum formalism for such experiments are accurate, then the physical world itself cannot be EPR local. The world itself is not. That's what I said in this paper. That's what they all get upset about. Bell didn't prove any such thing. So, in the sense that bothered Einstein, there is, in fact, spooky action at a distance. If you accept that the predictions of quantum theory are accurate. No. So that is what Bell did. Yeah, that's the conclusion, right? That's what Bell proved. And all of this other noise you hear, which you'll hear a lot of, about Bell having done something much less significant or just ruled out hidden variables or whatever, is not right. Now, hopefully, Lev is going to tell you that if you go many worlds, let me just say this about, I'm not sure what Lev is going to say. One way of understanding some of the many worlds people is that they will not even object to any of this reasoning, but in a way say, no, if you think the predictions of quantum, I'm including among the predictions of quantum mechanics, so let me say this directly. I'm including among those predictions that when you do an experiment, there's a unique result. There's one result. And so you can unproblematically talk about the correlations between experiments carried out far away. If whenever I do an experiment, I get all the results, it's not quite clear what you even mean by the correlations between distant experiments, okay? But I'm including among the predictions of quantum mechanics that experiments have unique results. Whether that means the many worlds you can think of as denying one of my presuppositions, whether that makes it a local theory is still an open question, because we have to then think through carefully why the world should appear as if there's only one result and how this all gets implemented. So I'm trying to keep enough room to have that discussion, which maybe we'll have later today. But on the assumption that, that experiments have outcomes, that's the argument, those are all the presuppositions, and that's what Bell did. Thank you.
Not in town. Not in town. made this place. It's made this place. It's lit.
Bless you! Bless you!
Bless you. Oh, bless you.
to recharge. I need more time. I need more time. need more time. I need more time.
It's locked. It's locked. Carrying too much. I'm carrying too much.
Would you like something? Would you like something appraised? Goodbye then. Goodbye then.
I can't make this right now. I can't make this right now.
of bandits. Be wary of bandits.
Vultures. Damned vultures. Is done. Fortune walks with you.